ZenoLink uses optical DLT technology to create a 6 degree of freedom, three-dimensional representation of whatever we're digitizing. One of the advantages to the methodology we use allows us to be able to digitize virtually anything that can be videoed with high speed or even standard video within a certain environment, within a certain space, and calculate not only the rotations but the linear displacements. So one of the advantages is with respect to movement and speed is we can digitize and calculate the displacement of an object as well as the speed and really the acceleration of an object in that space. So when it comes to golf, we can very simply digitize the club head, the center of the club head or some aspect of the club head, track it throughout the entire golf swing, measure its displacement in 3 dimensions as well as its linear speed or its speed output or miles per hour, as well as accelerations. We don't have to have a marker or a sensor or anything on the implement itself. That's nice in golf. It's also nice in other sports. Baseball swing, we can digitize the bat. Lacrosse, we can digitize the lacrosse stick. We can look at the tip of the stick. We can look at the center of the net. We can look at the base of the stick, whatever we want. We can digitize parts of the shaft to look at orientation of the shaft. In baseball, we can digitize the ball. We can digitize the wrist, the hand, not only the internal rotation speed, but how fast the wrist is moving at any point in time, the displacement of the wrist. So it's quite gives us a lot of versatility and accuracy with respect to measuring distal end speed, not only the angular components, the rotational components, but the linear components as well. So what we did recently was a fun little experiment to show, first of all, the versatility of what we do, and second of all, the process and also the accuracy with which we can measure linear displacement, the rate of displacement or velocity, and then ultimately acceleration from there. So what we did with this experiment, which is pretty cool, is we took our high-speed Casio cameras out to a back road, and we set up on this road, we set up our cameras on either side of the road, using 2 cameras to do our DLT measurement at about a 90-degree angle to the orientation of our calibration. We took out our box, our calibration box, which is a very small DLT object. We're only using 8 points. You can make these obviously bigger, more points. You can go 8, 16, 32. You can expand this out. The larger the volume, the greater the space in which you can accurately define movement. But believe it or not, even with a small space or a small DLT object, we're able to get quite a bit of effective radius around the DLT object where we can effectively and efficiently and accurately create the 3D model. So what we did was we took our cube out onto the street right in a certain section. We marked off a small space of about 20 to 30 feet, put the cube in the middle, put our cubes on either side of or our cameras on either side of the road. Took the cube out once that space has been calibrated now into X, Y, and Z. We took our car, literally a car, and we drove our car down the street, put a couple indicators, an X on the one part, a round ball on another part, some identifier that we could digitize very effectively. And we drove the car at a set speed through the zone. In this case, we set it at 27 miles per hour. And we filmed the car going through the space. Now what's cool about that is that we were able to do this. Now we don't have these cameras gen locked. I mean, obviously, if you have a control environment, you have a laboratory, you have your cameras set in positions, and you have a software that can literally gen lock the cameras and simultaneously fire both cameras at the exact same instant. That's great. But we can take our cameras filming at 240 hertz, and we can use a simple marker to synchronize the cameras and still get very accurate results. So this gives us a lot of flexibility. We're outside on a back road with 2 standalone cameras filming and digitizing a car as it drives down the street. What we did to synchronize is we actually had Andrew stand off to the side and view both cameras, and as the car came through the calibrated space, all Andrew did was sort of like a movie, take one, and we synchronized on the instant in which that clap occurred. We then digitized the car coming through the calibrated zone at 27 miles per hour, 27 set on cruise control, speedometer, and a GPS quantifying and confirming that we were exactly at that 26, 27 miles per hour right there. Drove through the space, and we actually digitized the car, digitized certain points on the car, and calculated the displacement through the zone, more importantly, the velocity or the rate of displacement or the speed at which the car drove through. We can break that speed into its directions. We can see how fast of that total speed was in the X, the Y, or the Z directions. In this case, it's almost all in the X direction. But we can look at not only the speed at which the car came through, but again, the three-dimensional direction of that speed. So how much of the 27 miles per hour was directed, let's say, X, which would be along the road? How much of that 27 miles per hour was directed left or right? How much was up or down? So we can actually look at speed in a very intricate, very involved way, but also a very simplistic way. And the nice thing about this, it kind of shows you that using this technology, using this modality or this version of the technology allows us incredible flexibility. I mean, we're driving a car down the back road off on a street and digitizing the car through a zone of calibrated space. And it doesn't get any more flexible than that. We're able to do that very effectively even without gen-locking the cameras. So what I'm going to do now is I'm going to show you some of the process that we went through, the video of the car coming through and the calibration process, and the data that came out of it to show you what we calculated in terms of speed through the zone, displacement, and three-dimensional components of the speed through the zone. And again, this is just showing you the flexibility of what we do, the accuracy of what we do, but also the practicality of what we do. Now we're not a launch monitor, we're not a TrackMan or a flight scope. We're not trying to meticulously define collision dynamics. And that's great. That's what TrackMan does. That's what FlightScope does. That's what a launch monitor does. That's what they're designed for. Well, all we want to do, whether it's a baseball swing, a golf swing, a lacrosse shot, a baseball pitch, a tennis serve, whatever it is to be able to relate body movements to some sort of outcome. The rotational as well as the linear output of the most distal end of that system, whether it's the club head, whether it's the lacrosse stick, whether it's the arm itself, a baseball being thrown out of the hand. We want to be able to correlate movement to speed and directional application of speed, displacement and the direction of movement. And we want to then correlate changes in movement to changes in outcome. And that's what we use this kind of technology for, that club head speed or that racket speed or the ball velocity or wrist velocity, whatever it might be, is a basic identifier of outcome, and we want to relate body movement changes and deficits and whatnot to certain aspects of outcome, and that's what we do. So let's go take a look at the data. Let's look at the video itself, the digitizing process, so you can kind of see what we did, and then actually look at the data to show you what the outcome was.
Okay, now we're actually going to look at the data collected. There's two different trials we'll look at real quick. One was data captured at 240 frames per second. The other was captured at 30 frames per second. Just to give you some basic comparison between the two. These are not the exact same trial. However, both were in both cases, the car entered the digitizing zone at 27 miles per hour. And again, we confirmed the 27 miles per hour with both the speedometer as well as the GPS system. So what I have here is a plot of the actual speed which the car was moving through the zone that we digitized, and then the direction of applied speed relative to the three-dimensional calibrated space. So the first thing we'll just take a real quick look at. Again, they're not exactly the same trial, so have to keep that in mind as you look. But this is a basic idea of what we're looking at here in terms of being able to calculate speed as a measure relative to body. Again, we're not trying to be a launch monitor. What we're trying to do is give reasonable, consistent data on clubhead speed or whatever the implement might be, whatever the body part might be. We're looking at distal speed, the rate of displacement. So we're calculating a point. We can calculate its three-dimensional displacement. We want to look at the rate at which the body segment or the implement is moving through the displacement, or the basic speed. So what we can see in both cases, we came in here at 27 miles per hour. There was a slope as we came in, and what you'll see is that as we came into the zone, we tracked, as we first entered into the zone, right about 27 miles per hour. And then as the car hit the slope, we started to pick up a mile or two as we hit the slope. And you can see what's interesting about that is when you look at the three-dimensional component, obviously the 240 frame per second is a little bit finer, more points to the same space. But what you see here is that the bulk of the speed obviously is along the intended direction, which was driving through, and I'll show you that in a second. But what you'll also see, in this case I drove a little bit more crooked than in this case, but some of that speed is moving left to right, but you'll also see the blue component go up over here. Graphs are a little small, so I apologize, but as the blue is going up, and I'll show you the way the calibration cube was lined up, that would indicate that the cube was laying on the street where there was a slope, and we drove through. As you drive through, you're going to see the cube sloped, and the car, the ball, or the digitizing point ran through the system, which would make it look like it was going up. So I'll show you, how that's going to sort of play a role. But what's nice is that you're able to identify speed consistently and accurately, but you're also able to see and identify components of speed, or the direction of applied speed. Again, you can see that this, let's just look here at the 240 hertz real quick. If you look, you'll see that you start to pick up some speed right where you start to see that variation in the slope, or the up and down speed, which is the sloping of the road downward just a little bit, which would tell us why is that speed increasing. So we see that is increasing our overall speed, but we can see what direction that speed is being applied, and it can give us some idea of why that speed is changing. So it gives you some pretty good information. So here's really quick. Let's just take a look at some of the video footage. Here's the calibration cube. Again, we're just using a small 8-point VLT, so we only have a limited space that which we can digitize accurately, and we mark that off with some chalk lines. What this is basically identifying is our direction of speed. So we have our X is this direction, our Y is this direction, and our Z is this direction. So we've now defined that space into X, Y, and Z components. So we can not only determine how fast an object is going, but we can identify what direction it's going and how much of that speed is applied in the different directions, up and down, in and out, or straight, or X, Y, and Z essentially. So that's our calibration process. Now I'll just show you a quick video of just basically the car itself, just to give you an idea of what we're looking at here. This is just a snippet of what we filmed. The car rolled through. Now remember, what we're looking at here is set up on our thing is our X, our Y, and our Z. So we've got our three components of speed. So what we're doing is we're digitizing a mark on the car right here, and we're watching that mark come through the space. And it's that slope. What you'll see is that as the you get a little bit of a positive Y. As the cube was placed on the slope, the car goes through that slope, you'll see the point actually go, because of the orientation of the cube, go into positive Y, and that's that slope. So This is the car moving through the space at 27 miles per hour. And lastly, what we'll show you here is just a bit of the process. So here we have some screen captures from our Vicon Modus system, which is what we use to create the raw data. And what you can see here is this is just one of the two views. We have to use two different views. You can use as many views as you want, 4, 5, 6, 8, or more. We're using just two to do this simplistic movement. We're digitizing a mark that's on the car, a nice identifiable mark, just like our elbow or wrist or the club head or any identifiable mark. We're digitizing that mark as it moves through the space. You can see here we can blow up the visual, which is helpful in some cases where we actually can zoom in on and get a better idea of. So if we're having if we have a small object that we're digitizing, or there's some reason that we need to see it more clearly, we can zoom up, we can adjust the contrast, we can do different things like that. And basically what you're going to see here is the digitizing process. You'll see the crosshair being put on the ball, zoomed up, you can see the movement, trying to find the center of the ball every time. And then you'll see that process. So essentially from both perspectives. We then take the raw 2D using DLT mathematics. Vicon converts that, and the calibration converts that into the raw 3D. And then we can either look at it in a raw unfiltered form, or we can choose to filter the content based on frequency spectrum analysis, which allows us to identify signal or valid signal content from noise. And that can be noise from any different, that can be marker jiggle, or it can be digitizing error, but there's a certain frequency of content where the primary signal is contained, and then we have noise, and we can use different digital filters, FFT, Butterworth, different ways that we can filter noise depending on what type of data signal we're looking at and what type of noise may potentially be impacting the quality of the signal. But again, we'll take a look again, last thing. So what we did then, and let's go, just real quick, let's go back. And so what are we looking at here and how we do this? Well, roughly, you can say from point A to point B, so let's just say this is a large space, A to B. You can say that the marker on the car moved X distance. And then if you look at the time it took to move that distance, you can calculate the average velocity from between point A and point B, or average speed. With 3 dimensions, you can do the same thing in X, Y, and Z. Look at the average velocity between A and B, and then do a resultant of the X, Y, and Z speeds to look at total speed output. As the faster, so you can go from 30 frames per second to 240. The faster the sampling, the smaller the spaces. So the less averaging. And then what you can do, as opposed to just doing an average, is to run a derivative formula. First derivative of displacement giving you what we call instantaneous velocity. Just taking that gap mathematically and taking the gap and basically squeezing it down to 0, which would be the easiest way to define what a derivative is. Fairly basic mathematics. We're not talking about anything really complicated, and that's pretty straightforward. So we can calculate the speed, the direction of applied speed, and the resultant overall speed, which is really nice, because when you're looking at an athletic movement, you're typically, especially in throwing, hitting movements, you're trying to accelerate some part of the system, either an implement, like a golf club or a tennis racket or a baseball bat, or a body segment, like the arm, the wrist, or if you're throwing something. If you're looking at cycling, for example, you're accelerating the pedal around the bottom bracket or along the crank arm. So you're looking at the speed at which that pedal is moving, both rotationally as well as linear. So any point that can be effectively identified and digitized can be tracked. Now, this is linear, and the nice thing about this 6 degrees of freedom means that we can track not only the rotations of of objects, but we can calculate the linear displacement, and then from the linear displacement, speed or velocity or rate of change, and then we can also look, or rate of displacement, and then we can see, or change of displacement, and then ultimately we can take velocity and take the next step, the rate of the change of velocity over time being our acceleration. So it's a nice calculation to be able to match outcome to changes in body if you're looking at performance or program enhancements in terms of movement. And it's also good to see when you have breakdowns in coordination, the impact on velocity. The nice thing about this, as I discussed in the office, is that we track this through the entire process. So we can see, a lot like if you go back here, if all you're looking at is one instant in time, let's say collision or ball release if you're throwing a ball, you only get that snippet of what the speed was and maybe what that applied direction was at that instant. What's nice about being able to track the entire motion is you can say, oh, well, we came in at a certain speed, the car sloped down, we gained 2 miles an hour, and by the time we hit here, we had improved our speed by 2 miles per hour, and we were accelerating because you can see the slope of that speed is going upward. So we were actually in the process of gaining speed. What if we came in high and started to slow down? Now we start to go up a hill and we start to decelerate. So our same speed has different characteristics in terms of how it was produced, which is specific to what is going on in the movement pattern, which is really important. Now, all you care about is what happened at a collision point or an instant in time, great. But if what you care about is how that instant in time was created, you want to see how things move in and out of that instant in time. Again, you could have the same 31 miles per hour, one coming off a deceleration mechanism and one coming off an acceleration mechanism. At the point of collision, the characteristics are the same for the most part in terms of the speed, the direction of the speed, let's say. But in terms of how it was produced, and that's what we're looking at, is how the body's producing this stuff, has a huge impact. You also look at efficiency. If you're looking at, did the body produce more speed prior to an impact or an instant in time and lose speed going into that, or did it continue to accelerate and produce speed at its optimal level? Was this the peak speed or was it something less than the peak speed? That kind of stuff can be assessed. Now again, our goal with this data is to be able to assess that relative to body motion. Our primary focus is gross movement pattern or activity-specific coordination. So hopefully this was an interesting way to start to identify and understand how three-dimensional data is produced and how three-dimensional data, six degree of freedom dimensional data is applicable and usable when looking at not only human motion, activity-specific coordination or gross movement pattern, but also the outcomes of that motion relative to implement or different body segments relative to speed produced as an outcome of the body movements.